Hi viewers, my name is Pete Mattock and this is the latest of my series of videos exploring the maths behind the sorts of tips and tricks that students might be taught in class or might pick up on the internet. The internet in particular is awash with these maths acts, and if anybody knows anything about me and my work, you'll know that I'm very passionate about students not only being able to do maths, but understanding the concepts that underpin why these mathematical ideas work. And today I've got a lovely trick, which is about approximating the square root of whole numbers. So say, for example, something like the square root of 29. Now, 29 is not a square number, so we can only ever get a decimal approximation of the square root of 29. And of course, you could just reach for your calculator and ask your calculator to give you quite a good decimal approximation of the square root of 29. But there is a nice sort of trick which allows you to get a reasonable approximation for this number without the need of a calculator at all. And the way it works is to say, right, well, if we look at 29 and if we know our square numbers, then our square numbers will tell us that 25 is the closest square number below 29. Yeah, 36 is the next square number, but that's above 29, that's too big. And the square root of 25 is 5. Now, what that tells us, of course, is that 29, if we want to get a decimal approximation for the square root of 29, is going to be 5 point something. And, it might be quite difficult, or you might have thought it would be quite difficult to get this point what without the use of a calculator, but it turns out there's a nice little trick that allows you to get at least normally the first digit bang on. And the way this trick works is this: it says, right, well, if it's going to be 5 point something, let's not do point something for it. Let's do the fraction first. So we're going to set up a fraction here. So it's going to be 5 and some fraction. And the way we're going to form that fraction is to do 29 minus 25 for our numerator. And then our denominator is going to be simply 2 times 5, 2 times this 5 here. And then if we now work out this fraction, the numerator and denominator, that gives us 5, and 29 minus 25 is 4 on the numerator. 2 times 5 is 10 for the denominator. And so we've got 5 and 4 tenths, which is 5.4. And it turns out that that is actually quite close to the square root of 29. If you were to ask your calculator for a decimal approximation, the decimal approximation your calculator will give you will be about 5.385-ish. Okay? But again, 5.385 rounds to 5.4 when you round it to one decimal place. So to one decimal place, those both give you the same thing and are both decimal approximations of the square root of 29. And we can do this with anything. We'll see another example here. Let's say we want to work out the square root of 70, or at least a decimal approximation to the square root of 70. Then again, if we know our square numbers, we know that 64 is the closest square number below 70. And we know that the square root of 64 is 8. So this root 70 is going to be 8 point something. And then, so how do I work out the something? Well, we're going to deal with this same fraction, 70 minus 64 on the numerator. And then because it's an 8 here, 2 times 8 this time on the denominator. And that gives us 8, and 70 minus 64 is 6. 2 times 8 is 16. So 8 and 6/16. 6/16 simplifies to 3/8. So we've got 8 and 3/8 as our rough approximation. And 8 and 3/8 is 8.375. And again, if you ask your calculator what root 70 is, or to give you a decimal approximation of root 70, your calculator would say 8.3666. But again, both of those round to 8.4 when you're rounding to one decimal place. So this trick does seem to give you at least good approximations to what if you round them to 1 decimal place each time, assuming you need to round it at all. Sometimes you don't need to round this one at all. So that's the trick, and it's a lovely trick. But the question is, why does it work? Well, in order to show you why it works, we're going to do a little bit of graph drawing. So I'm going to just do a sketch. We don't need to draw it accurately. I'm just going to draw a sketch of the y equals x squared graph. So here's x axis and here's my y axis. And in the positive quadrant, y equals x squared looks a little something like this. Okay? And if we track what's actually going on here, we're going to take that first example again. If we track what's going on here, then what we're saying is, well, we've got a value of 29. And we're trying to find the x value that makes that happen, that when you square it, gives you 29. And then from the line underneath, we're saying, well, one of the things we definitely know is that 25 is not far below 29. And 25, when we square root that, gives us 5. So 5 squared is 25, or the square root of 25 is 5. And then actually what we're saying here is, and this is the sort of crux behind this method, is that if we take this point 525, that's not quite on the graph, I've sketched it, but you get the idea, and we draw a tangent to the graph at that point, we'll make it there, tangent to the graph at that point, and we extend this 29 across to where it meets the tangent and find the value of x there, that x will be closer to the value I'm trying to find than that 5 will be. And that will be a better approximation to the actual value. Remember, this is the actual value I'm trying to find, but this x, if I can find this, will be closer than that 5. And so, okay, how do we find that x? Well, to find that x, we're going to use the form of the equation of a straight line, a form of the equation of a straight line. We're not going to use y equals mx plus c. We're going to use y minus y1 equals mx minus x1. And in this country, at least, in England, that's a form of the straight line equation that students aren't normally introduced to until A-level, but it's a quite simple consequence of finding the gradient of a straight line, changing y over changing x, slightly rearranged. So it shouldn't be a problem for students below A-level to grasp where that equation of the line is coming from, okay? Or that form of the equation of the line. So what we're going to do is we're going to substitute some values in from our graph here into this equation. We've got two y values here. We've got a y value of 29, and we've got a y value of 25. And then we've got two x values here. We've got x is x here, and we've got x as 5 here. And then it's about this m. What is this m here? What's this value of m? And this is where we do need a bit of more advanced mathematics. In particular, we need a bit of calculus, because what we need to know is the gradient of this tangent is the same as the gradient of the curve at the point where the tangent meets the curve. And we need to know that for y equals x squared, the gradient of that graph at any point along it is given by 2 times the x value at that point, i.e. that y equals x squared differentiates to dy by dx equals 2x. And that's definitely the sort of thing that you'd only introduce, certainly in this country, at A-level, or if your students were doing the level 2 further maths qualification. But given that we know that, then we can say, right, well, the gradient of this graph at this point here is twice the x value, so that is actually 2 times 5. And so we've got 29 minus 25 equals m, which is 2 times 5, x minus 5. And now all we're going to do is rearrange that. I'm going to divide both sides by 2 times 5, first of all. So I've got 29 minus 25 over 2 times 5. And I'm deliberately not evaluating these things at this point, so you can see how this ties back to what happened before. That frees up this bracket, so we've just got x minus 5. And then I'm going to add 5 to both sides, so we've got 5 plus 29 minus 25 over 2 times 5 equals x. And you can see this is exactly what we got up here, 5 and 29 minus 25 over 2 times 5. And so that graphical approach of finding the tangent and the x value from the tangent being closer to the true x value than our starting value of 5, and rearranging the equation of that tangent is why this hack works. Now, for those of you that teach A-level, you might be thinking, wow, that looks an awful lot like Newton-Raphson. And it turns out this is sort of the precursor to Newton-Raphson. And it's a lovely way both to introduce the idea of the Newton-Raphson method, but also to sort of come back to this when you've studied Newton-Raphson and show again why it works using the Newton-Raphson approach. And, to turn this into Newton-Raphson, all you'd have to do is drop this down until this point that you were trying to find became a root of the equation. So plot the graph y equals x squared minus 29, and it becomes using Newton-Raphson to solve that equation, if you like, or to get the first iteration to get a better approximation to the solution. So, a lovely trick, being able to approximate the square root of a number without a calculator, but the maths behind it, except for this little calculus bit, is actually a lovely way of tying in sort of the y equals x squared graph, and drawing tangents to graphs. And if if your kids don't know the calculus, then you might have to fudge this little gradient bit by just telling them that it's 2 times whatever the x value is. But there's a level of understanding we can reach there about what's happening with this trick. Thank you very much for listening. My name has been Pete Mattock, and do stay tuned for more episodes of Understanding Maths Hacks.